Derivation of Nernst equation to calculate non-standard state cell potential. Not standard state cell potential. Derivation of Nernst equation to calculate non-standard state cell potential, not standard state cell potential. So let's get started. Derivation of Nernst equation to calculate non-standard state cell potential. First of all, let us draw a galvanic cell. Here, in the first compartment, solution of zinc sulfate has been taken, and in the second compartment, solution of copper sulfate has been taken, a kind of galvanic cell, which is actually Daniell cell. Daniell cell is an example of galvanic cell. In the zinc sulfate solution, metallic strip of zinc is submerged. In the copper sulfate solution, metallic strip of copper is immersed. Now, these two metallic strips are connected with wire with a galvanometer. This is galvanometer. Galvanometer shows the presence of electricity. Now, these two solutions are connected with a salt bridge. Now, this is a complete circuit. Here, zinc is more reactive than copper. Zinc is more reactive than copper. So, zinc bar acts as anode and copper bar acts as cathode. That is, zinc bar produces electrons and copper solution, copper ion accepts that electrons. Here, zinc atoms go to the solution as zinc 2 plus ions and copper ions deposit on the surface of the cathode as metallic copper. Here, the cell reaction is metallic zinc, copper ion, transfer of 2 moles of electrons, then zinc ion and metallic copper. So here, transfer of 2 moles of electrons occurs. Now, suppose this cell is in standard state. That is, solutions are of 1 molar and the system is conducted at 25 degrees Celsius temperature. This is standard state of the cell. When the cell is in standard state, then very easily we can calculate standard cell potential in this way. That is, standard oxidation potential of anode plus standard reduction potential of cathode. This is one equation. Another equation, standard oxidation potential of anode minus standard oxidation potential of cathode. Here, cathode's oxidation potential. We have another equation, that is standard reduction potential of cathode minus standard reduction potential of anode. These three equations by which we can calculate standard cell potential of Daniell cell. When the cell is in standard state, then we can calculate standard cell potential easily, because these values are obtained from electrochemical series of standard reduction potentials of electrodes. Suppose we know standard reduction potential of copper is plus 0.34 volt minus standard reduction potential of zinc is minus 0.76 volt. Then here standard cell potential of Daniell cell is 1.1 volt, which is obtained very easily when the cell is in standard state. But when the cell is in not standard state, that is, concentration of solution is any concentration and any temperature, then how we can calculate non-standard state cell potential? Non-standard state cell potential in this way: non-standard state oxidation potential of anode plus non-standard state reduction potential of cathode. This is one equation. Another equation: non-standard state oxidation potential of anode minus non-standard state oxidation potential of cathode. Another equation: non-standard state reduction potential of anode minus non-standard state reduction potential of cathode. Non-standard state reduction potential of cathode minus non-standard state reduction potential of anode. Here these values are not known, that is, standard state oxidation potential of anode, this is known, plus 0.76 volt, and standard state reduction potential of anode, which is minus 0.76 volt. That is, when the cell is in standard state, then these values are known. But when it is in non-standard state, then oxidation potential is not known and reduction potential is not known. Similarly, here, if it is in standard state, then reduction potential is known, which is plus 0.34 volt, and standard state oxidation potential, which is known, minus 0.34 volt. But when it is non-standard state, that is, oxidation potential is not known and reduction potential is not known. Now, here, this is non-standard state cell potential. If we want to calculate non-standard state cell potential, if it is in non-standard state, then we have to know values of non-standard state reduction potential of electrode, that is non-standard state reduction potential of cathode, and non-standard state reduction potential of anode. Now, let us see what is non-standard state reduction potential of cathode and non-standard state reduction potential of anode. Non-standard state cell potential is equal to non-standard state reduction potential of cathode minus non-standard state reduction potential of anode. This is the equation to calculate non-standard state cell potential, but these values are not known. Here, scientist Walther Harman Nernst established a relation between non-standard state reduction potential of electrode and standard state reduction potential of electrode. This is the relation between non-standard state reduction potential of electrode and standard state reduction potential of electrode, which is established by German chemist Walther Harman Nernst in the year 1889. What is that relation? First of all, let us see this non-standard state reduction potential of anode. Here, when the cell is in non-standard state, then what will be the reduction potential of zinc electrode? The relation is standard state reduction potential of anode, which is known, plus RT by NF, then ln concentration of zinc ion. Here, N number of moles of electrons transferred. Here N is equal to 2. So here 2 can be put instead of N. Generally we can put N. This is the relation between non-standard state reduction potential of electrode and standard state reduction potential of electrode. This relation is established by scientist German chemist Walther Harman Nernst in the year 1889. Again, let us see this one. Non-standard state reduction potential of cathode, which is standard state reduction potential of electrode, that is cathode, plus RT by NF, then ln concentration of copper ion. This is the relation established by chemist Nernst, German chemist Walther Harman Nernst in the year 1889. This is the relation. Now, let us put values of non-standard state reduction potential of anode and non-standard state reduction potential of cathode in equation 1. Then we can write non-standard state cell potential is equal to this one, non-standard state reduction potential of cathode, that is this one, standard state reduction potential of cathode, then here plus RT by NF ln concentration of copper ion. Then value of non-standard state reduction potential of anode, that is this value. Here there is minus, so minus. Then this one, standard state reduction potential of anode, plus RT by NF ln concentration of zinc ion, non-standard state cell potential. From this equation we can write non-standard state cell potential is equal to, here this is standard state reduction potential of cathode. Then let us take this one, minus standard state reduction potential of anode, minus RT by NF. RT by NF is common here, plus RT by NF is taken common. From this is left ln concentration of copper 2 plus ion, this one, minus this one ln concentration of zinc 2 plus ion, taking common RT by NF. Here value of N is 2. Now this one is standard state cell potential, which is known, plus RT by NF. Here ln A minus ln B, then ln A by B, concentration of copper 2 plus ion divided by concentration of zinc 2 plus ion, following ln A minus ln B formula. This is the equation we got. Again we know ln is equal to 2.303 log. Now replacing ln by log, we can get standard cell potential plus RT by NF. Here 2.303 RT, molar gas constant, and Kelvin temperature, number of moles of electrons, this is Faraday. Then here we will write now log concentration of copper 2 plus ion divided by concentration of zinc 2 plus ion. This is now complete Nernst equation to calculate non-standard state cell potential. Now let us write complete equation. Complete Nernst equation. Non-standard state cell potential is equal to standard state cell potential, which is known, plus 2.303 RT by NF, then log concentration of copper ion for Daniell cell divided by concentration of zinc ion. This is Nernst equation, complete Nernst equation to calculate non-standard state cell potential. Here, log concentration of copper ion, that is actually log concentration of metallic zinc and concentration of copper ion divided by concentration of zinc ion and concentration of metallic copper. But when this is solid, its activity is 1. Its activity is 1. That is why here is actually log concentration of copper ion times concentration of metallic zinc, but its activity is 1. That is why it is not written here. Divided by concentration of zinc ion and concentration of metallic copper, but its activity is 1. That is why it is not written here. Actually, it will be times concentration of metallic zinc, its activity is 1, times concentration of metallic copper, its activity is 1. That is why these two are not written. So this is Nernst equation to calculate non-standard state E cell. Derivation of Nernst equation to calculate non-standard state cell potential or non-standard state cell voltage. Thank you for watching.